Hello again, everyone. I'm recording a video again because the first time didn't work because my iPad was updated and it turned the microphone off without my knowledge, but hip hip hooray, here we go once again. All right, so this first lecture is going to be brief, and it's meant to just be a brief recap of simple harmonic motion with springs and pendulums to give you guys a sort of reorientation to what we're talking about. So we're just going to kind of review what we did at the end of last week. Now when we talk about a mass spring system, it oscillates back and forth, and so we have this spring right here, and that spring is going to be characterized by a constant K. K is a measure of how strong the spring is. It's measured in newtons per meter. So the stronger the spring, the faster the system will oscillate. With that said, the mass, m, right here, is of course related to the inertia of the system, so a heavier mass is going to make things move more slowly, and of course m is measured in kilograms, like always. With that said, what we're envisioning here is if we pull this mass back this direction, then it's just going to, when released, it's just going to oscillate back and forth like that forever. Now, if there were friction, of course, it wouldn't go forever because the friction would slow it down, but there's not friction. We're going to assume it's frictionless, and so it just goes back and forth forever. With that in mind, we last week learned that the time for this to occur with a mass spring system is characterized by this equation right here, and we call that the equation for the period. T is the period, and it's measured in seconds, and that is equal to 2 pi times the square root of m over k. So that's a quick recap of the period of a mass spring system, and the force of that spring system right there is equal to negative kx, where k, of course, is the spring constant, and x is the distance the spring has been stretched or compressed, which is measured in meters. And note here that this right here, x max, would be when the mass is pulled all the way back there, and that is the maximum distance, the maximum displacement, and we call that the amplitude, okay? And something that a lot of people struggled with a bit last week is remembering that there are 4 amplitudes per period. So if I pull this mass back and then I let it go and it goes back and forth, well, one period is the time for one complete cycle, and one complete cycle is the amount of time it takes to go back and forth. So if we count up the number of amplitudes, we have 1, 2, 3, 4 amplitudes per period, and that is just an important little thing to remember, is that there are 4 amplitudes per period there, okay? So with that said, that's a brief recap of a mass spring system. We're going to go ahead and move on to pendulums. So a pendulum is just a mass right here on the end of a string, and in this case we see the string is right there. It has a length L, so we have the length L for the pendulum. The amplitude or displacement, I should say, of that pendulum is the angle theta, so that is the displacement from equilibrium. Equilibrium being this vertical line here, and the equilibrium line, that's not very straight. Let me go ahead and see if I can get a vertical line. There we go. So that vertical line there is where we measure the equilibrium from, or the displacement from, and theta is, of course, going to be an angle, so that's going to be measured in either radians or degrees. So radians is the SI unit for that, standard unit. Anyway, as you can see here, we have the equation for the period of the pendulum. The period of the pendulum t, which is once again measured in seconds, is equal to 2 pi times the square root of L over g, where L is the length of the pendulum and g is the acceleration due to gravity. So, interesting thing here is that the amplitude does not come into account with the equation for the period of the pendulum. So you'll notice that theta here does not appear anywhere in this equation. So the time it takes for the pendulum to oscillate back and forth only depends upon 2 things, and that is the length of the pendulum and the acceleration due to gravity. So if we're on Earth, well, that of course fixes the acceleration due to gravity, so the only thing we can do to change the period of a pendulum here on Earth is to change the length of the pendulum. That's all we can do. And with that said, I want to talk about the force that brings the pendulum back to equilibrium for a moment, and that of course is the force of gravity down here, but you see it's not the entire force of gravity. If it were just gravity, then the force bringing the pendulum back to equilibrium would be mg. But of course it's not. It is not just mg, it is only a piece of mg. So the question is, okay, well, what do we mean a piece of mg? Well, we mean a component of mg. So you might remember back when we did inclined plane, we had a downward force of gravity here, and then we broke that into components that were parallel and perpendicular to the incline. And that's basically what we have here. It is only the part that is inward right here, this piece of gravity, that we're actually concerned about. And I'll spare you the geometry, but in short, to calculate that gravity using trigonometry, we end up doing this equation right here, and that is mg sine of theta. So we call that the x component of gravity. It is the part of gravity that brings the pendulum back to equilibrium, and it is calculated as mg times the sine of the angle. Now, just a reminder, if your angle is measured in radians, then you need to make sure that your calculator is in radians, and if your angle is measured in degrees, then you switch it back to degrees. So your calculator just needs to match whichever form of the angle units you have to use. So that'll be the end of this brief lecture here, and the next lecture is going to introduce the concept of energy once again. So we're going to go ahead and stop.